Now that we have developed our reliable data transfer protocol and saw two strategies, namely go back and selectively repeat to improve the efficiency of our reliable data transfer protocol, let's now start seeing the actual TCP, how TCP packet is organized, how data is sent from one end to the other end using TCP. To start with, let's talk about something which is always invariably mentioned in all introduction of TCP. Everywhere we will be reading about TCP, we will face this line which mentions that TCP is connection oriented. Now let's try to understand what is the meaning of this particular aspect which mentions TCP is connection oriented, which is in contrast with UDP, which we have already discussed, where we saw that UDP is connectionless. So two protocols of transport layer, UDP is connectionless, TCP is connection oriented. Now remember, the exact word is connection oriented. It is in contrast with the word connected. Now these are two different words. It is not said that TCP is connected. It is said that TCP is connection oriented. Now let's try to gauge what can be the meaning of this particular introduction which says TCP is connection oriented. Let us for a moment go back to the very initial discussions when we discussed about circuit switching and packet switching. If you remember the discussions about circuit switching, where a circuit is a dedicated path between two different machines or two different nodes. Say A and B are two different machines. There are multiple paths that go from A to B, and when we say that A and B is transmitting data, or they are communicating over a connection using circuit switching, it means that a particular connection, a dedicated path is created between A and B for that particular duration. That means we create a circuit, say this particular circuit is created, that means this particular path is dedicated between A and B, and every message, every communication, every packet, every data will flow from A to B using this path for that particular session. This is circuit switching. That means a particular circuit is created between A and B. When we are talking about packet switching, when we are talking about internet, when we are talking about TCP, when we say that TCP is connection oriented, it absolutely does not mean this. Be very clear. A lot of people make this mistake when they say that TCP is connection oriented. They say that a particular connection is created between A and B. This connection is absolutely different from a connection as used in circuit switching. Circuit switching means a particular path is dedicated for that particular duration. When we use TCP or UDP, be very clear. The data can flow through any path. That means if A and B is sending data using TCP, some packets may flow through this path, some packets may flow through this path, some packet may flow through this path depending on the routing algorithm. That means no path is dedicated between A and B as in circuit switching. So A and B, when using TCP, they are not connected, just like in circuit switching. Unlike circuit switching, they create a session, but this session does not mean they are connected. There is no dedicated path between A and B. Then why it is called connection oriented? It is called connection oriented because these two nodes A and B creates a sort of session which acts as if these two sides, these two processes are connected. They are loosely connected. They are not connected through a path. They are loosely connected. This means that two steps. First step, before A and B starts communicating, before A and B actually starts transmitting the data that is being received from the application layer, they do some sort of handshaking. Now, what is the meaning of handshaking? Just like when two people meet, before they start speaking about a particular topic, they say hi, hello sort of things to each other. Handshaking is just like that. Say some data from the application layer of A is coming to its transport layer. Now A wants to transmit those data from A to B using TCP. Now before actually transmitting the data which is received from the application layer, A would create certain handshaking with B. What's the meaning of creating handshaking? Handshaking means A will send some sort of messages before sending the actual messages, before sending the actual data. That means just like saying hi and hello, A will send certain particular data packets to B, B will send certain data packets to A. What those data packets are, we'll see when we'll discuss how to create TCP connections. And once this handshaking is over, then the actual data transmission happens. That means before sending the actual data, A and B do some sort of handshaking. We'll discuss this aspect, what is handshaking, in detail when we talk about this TCP packet. But understand that TCP is connection oriented in the sense that before transmission of data, A and B do some sort of handshaking between them, and once the handshaking phase is completed, then only A and B starts communicating. They start actually transmitting the actual data. The other thing is, because TCP provides a lot of services. What are those services? We have already seen certain services like reliability. So when it wants to provide this sort of services like reliability, to provide reliability, it uses things like retransmissions, which we have seen in our development of reliable data transfer protocol. So to provide these services, it has to allocate certain variables and certain buffers in both the sides. That means when A and B are communicating over TCP, A will initialize and use certain variables in each side, B will also initialize and use certain variables at each side, A will also initialize and use certain buffers in each side, same with B, it will also initialize and use certain buffers at its sides. Now you may be wondering what's the use of these variables and use of these buffers. We'll see when we discuss about these things in detail. Just for an example, say we have already seen that TCP would be using a retransmission. So if A has sent a packet to B using TCP, now if such a situation occurs that A needs to retransmit that packet, that means A needs to keep that packet in a buffer for a certain amount of time. We'll discuss about these variables and buffers as we go along. Now evidently, just to start with, so if A and B are communicating with using TCP, understand that A will first send certain handshaking packets to B, and after sending those handshaking packets, a session will be created which we call as a TCP session, and then A will start sending the messages using packets to B. Now all these packets, all these TCP packets, whether they are handshaking packets or packets that contain data, these packets follow a particular structure, and today we are going to start discussing about this TCP data packet structure. This is the TCP packet structure. If you have gone through the UDP segment structure, which we had already discussed, you might see the very first difference. UDP segment structure was much simpler. Now if you look at this TCP packet structure, there are a lot of information. Now as in case of UDP segment, this TCP packet is again composed of two parts. One part which we call as the header part, header information, and the other part, the actual data part. Now what is this data part? This is the data that comes from the application layer. Whatever data comes from the application layer, that data is inserted in this data part. So you may require one packet, two packets, you may require many packets to for those data that comes from the application layer. Now with each of these packet that is created by TCP, this part which we call the header part, this part is always present in that particular packet. Now the first major difference between a UDP segment header and TCP packet header is that whereas the UDP header information is of fixed size. If you again remember the UDP header size, the UDP header size was fixed as 8 bytes. There are only 8 bytes of information in the UDP header. What was those information about? The source port, the destination port, the UDP length, and the checksum. only those 4 header information were present in the UDP segment. Now if you look at this TCP packet, you have many more information. Some of the informations are similar. For example, the source port, the destination port, this section, these are some of the information that was also present in the UDP segment. Now apart from this, you can see many other information. So the first difference, as we saw, that there is a field which we call as options in the TCP header. Now this options is variable. That means these options may be present or these options may be absent. When options field is not there, that means it is of 0 bytes. There is no options present. Maximum it can go up to 40 bytes. What are these options? We will see later on. Now because of this variable field of options, this TCP header field is variable in size. From here, starting from source port to this urgent data pointer, this size is of 20 bytes. This particular byte is of 20 bytes. This particular header part is always present. So 20 bytes of header information is always present in the TCP header. Source port number, destination port number, sequence number, acknowledgement number, and all these other header fields up to this urgent data pointer. We'll discuss all these in detail. So up till here, it consists of total 20 bytes of informations. If we add all this up, 16 bits, 16 bits, another 32 bit, 32 bit, 16, 16, 16, 16, all these account for total 20 bytes. So starting from this point to up to this point, this is 20 bytes. So 20 bytes of header information is always there. Apart from that, you have this options field which range from 0 to 40 bytes. So if there are no options field, that means TCP packet will have a header size of 20 bytes. Now if there are options fields, then obviously the size of TCP header will increase. If say I have 10 bytes of options field, then the header size will be 20 plus 10, 30 bytes. Clear? So these options will make the TCP packet header size variable. Now for most of the cases, for most of the communication, this option field is absent. This option field is very rarely used. We'll see in what context this option field is used, but most of the times a TCP packet will not contain this option field. That means the option field is of 0 byte. That means for most of the cases, the header size of TCP is 20 bytes. For most of the cases. But when in cases where option field is present, this size will vary. Clear? And again, remember, the options fields needs to be a multiple of the byte size. That means your options cannot end here. So it has to be, it can use 2 bytes here, under 2 bytes here, under 2 bytes here, under 2 bytes here, up to 40 bytes. So it should be a multiple of bytes. It cannot be ending in between, say somewhere here or somewhere here like this. So if it happens like this, it has to be padded with extra zeros. These things we have already discussed in UDP. So apparently the TCP packets, in the TCP packet, 20 bytes of header information always present, and depending on the options you can have some more header information. So if someone asks you what is the header size of TCP, you should say that it is variable. 20 bytes of header information is always there. There is under option fields which vary between 0 to 40 bytes. Most of the cases the option field is not present, so TCP packet will always invariably have 20 bytes of header information, but if this option field is there, then the header size will increase. So apart from this header field, then you will have this data field where you will insert the data that comes from the application layer. So before discussing the header fields one by one, let's have certain definitions. The definition we'll discuss is something known as maximum segment size, which is popularly written as MSS. So the maximum segment size is the maximum amount of data specified in bytes that can be inserted in the TCP packet's data field. Let's go back to the packets. So this is the data field. So how much data that can be inserted in this data field is given by this MSS. So, and this MSS is specified in bytes. So if it is, if we say that MSS is say 40 bytes, that means in this particular packet 40 bytes of data can be inserted in this particular packet. So depending on the MSS, the maximum segment size, it decides what amount of data we can place inside the TCP packet. Now, the default TCP maximum segment size is 536. So if you do not make any change, the amount of data that can be inserted in a TCP packet by default is 536. That means if say 1000 bytes of data come from my application layer, and because the default TCP maximum segment size is 536, that means I cannot place all the data in one single packet, because in one single packet I can place by default 536 bytes of data. So in this case, if I have 1000 bytes of data coming from the application layer, I have to divide the data into two packets. One packet will contain 536 bytes, the other packet will contain the remaining bytes. Now this is a default maximum segment size. The two sides can negotiate a different maximum segment depending on their capabilities. If they are capable of using a different maximum segment size, same higher maximum segment size, they can negotiate at the beginning. When they negotiate, we'll see later on. But they can negotiate saying that let us use a maximum segment size of say 1000. So if both the parties agree, they can use a different maximum segment size. But again, this maximum segment size will depend on their different processing capabilities. So if they can if they can use a different bigger maximum segment size, they can always use it. But the default TCP maximum segment size is 536. But even then, in most of the cases, this maximum segment size is not used. It's very rarely used. If you see the size of a TCP packet, we'll later see using some packet tracers to capture packets, and we'll see how a TCP packet actually looks like. You'll see that most of the times even this 536 bytes is not used. It's much lower. And you can have packets with even 1 byte of data if you use telnet. Because we have used telnet in some previous examples using certain tools when we discuss applications layer. In that case, sometimes very small amount of data is sent. So when we're sending very small amount of data or using certain tools, you see that we do not even use this maximum segment size. A very small amount of data is present. So it is not necessary that you fill data that goes to this maximum segment size. You can fill data up to that size, but the minimum is anything. Even there can be packets which have no data. You can send a packet without any data. You can simply send the header information without any data in that packet. So maximum segment size is the maximum limit. Minimum you can have anything, but you cannot cross that maximum segment size. Now here comes the role of another unit which we have discussed in UDP also. This is something known as maximum transmission unit. If you remember, maximum transmission unit gives the maximum size of a frame that can be transmitted using the data link layer technology, because the data is actually transmitted after the data link layer using certain technologies. So there are different technologies which are used for transmitting data, and depending on that technology, the maximum transmission unit varies. Now you may have a case where your maximum segment size is 1000. That means you can place 1000 bytes of data in your packet header, and if your maximum transmission unit is say only 500 bytes, in that case you cannot use this maximum segment size, because the maximum size of a frame that can be actually transmitted in the data link layer is 500 bytes. So in that case, even if MSS is of 1000 bytes, you have to follow these limitations of MTU. Clear? If it is not clear, let's again understand this using a concrete example. Okay, let's see this very simple example. Say the application layer sends 2000 bytes of data, 2000 bytes of data to the transport layer. Now the transport layer has a maximum segment size of say 2500 bytes. Clear? That means 2500 bytes of data can be inserted in a packet. That means all these 2000 bytes of data can be easily inserted in this packet. What is the header size? Say no options is used, so header is 20 bytes. Because we are using TCP, 20 bytes of header information will always be there. Options are not present. If options is there, then this header size will increase. So the packet size ultimately will be 200 bytes of application layer data and 20 bytes of header information. Now because the MSS is 2500 bytes, all the data can be easily inserted. That means the whole packet will be of size 2020 bytes. But now say the MTU is 1500 bytes. What does MTU indicate? MTU indicates the size of the frame that can be transmitted using the data link layer technology. Now 1500 bytes is the MTU of Ethernet. So if you're using Ethernet, it has got an MTU of 1500 bytes. Now remember this packet which has been created, size of the packet is size of packet. If I do not consider anything about MTU, that is 2000 bytes of application layer data plus 20 bytes of header information. 20 bytes header, this is, so this makes 2020 bytes. Now remember, this packet will further go to network layer, and then from the network layer it will go to the data link layer, and from the data link layer it is actually placed on the medium. It is actually placed on the medium through which the data will flow through the other end. Now when we discuss network layer again, we'll see that network layer also adds its own header. We'll later see, but network layers also add its own header. Now for to discuss this example, let's say the network layer adds 20 bytes of another header. 20 bytes of header. How much header and the network layer inserts, we'll see when we discuss a network layer later on. But just for assumption, let's assume that the network layer adds 20 bytes of header information after the packets goes from the transport layer to the network layer. Once it goes from the network layer to the data link layer, the data links layer adds some more header information. Now let's just assume that the data link layer adds another 20 bytes. Just for this example, sake of this example, let's assume that the data link layer adds another 20 bytes of header. So what's the total header information now has been inserted? Has 20 bytes by the transport layer, 20 bytes by the network layer, and 20 bytes by the data link layer. That means 60 bytes. 60 bytes of total header information. Total header information is there up till data link layer. 20 bytes in the TCP, 20 bytes in the network layer, and 20 bytes in the data link layer. 60 bytes of header, and apart from that 2000 bytes of data. So the total frame size that will be created in the data link layer would be of 2060 bytes. At the transport layer it was of 20 bytes, another 20 bytes of header inserted in the network layer, and another 20 bytes in the data link layer. So apparently the total frame size that is being finally created at the data link layer is 2060 bytes. Now what is the MTU? MTU is only 1500 bytes. So this data packet cannot be sent over this particular link. That means whatever be the final frame, that final frame has to be within this 1500 bytes. So how much data should we insert in the transport layer here? Now this would be easy because we now already know that total 60 bytes of header information. 60 bytes of header information would be there. Clear? And the total MTU is 1500 bytes. That means data that can be inserted in the transport layer is how much? 1500 bytes is the maximum size, minus we already know that 60 bytes of header information should be there. 60 bytes of header information would be there because 20 bytes in the transport layer, 20 bytes in the network layer, 20 bytes in the data link layer. So whatever be the size, whatever be the answer, let's see what is the. So if we subtract this is 1440 bytes. That means apparently the TCP packet which we have created in a transport layer, it can contain only 1440 bytes. Though the maximum segment size is of 2500 bytes, we cannot insert this amount of data because the M2 is 1500 bytes and this amount of header information would be there. So the data that can be inserted is only of 1440 bytes. That means the subsequent bytes we have to insert in a new packet. So we have to actually, in this example, we have to create two packets, one containing 1440 bytes and the rest containing 2000 minus 1440 bytes. So two packets has to be created in this example. So remember, though MSS will be given, you have to also see the MTU. So the amount of data you can actually place in a TCP packet, this cannot, first it cannot exceed the MSS, this should be obvious, but again, even it may be possible that you cannot insert that amount of data that has been specified by the MSS, because your MTU may not allow you to insert that amount of data. So after discussion about MSS, let's go back to our TCP header format and let's start discussing the header fields. Now, three header fields, specifically source port number, destination port number, and checksum, and the characteristic of these three header fields are similar as in UDP. The way these three fields are used, source port number, destination port number, checksum, the way they are used in UDP is exactly similar as in TCP. So we will not discuss them in detail here. I urge you to go through the lectures of UDP to understand how these different, at least these three header fields are used in UDP. To have a very quick understanding, quick summary, the source port number and destination port number is used for multiplexing and demultiplexing. Both are 16-bit field. So we use 16 bits to indicate the source port and the destination port. So source port identifies the port of the sending application and the destination port identifies the port of the receiving application, of the other side. So just for an example, say a machine A is sending, a machine A is sending a request to machine B and B is a web server. So A is sending a request to B and B is a web server. Because B is a web server, it will be using port number 80. Remember, your application uses port number 80 and A will use a random port number. Again, we have discussed all these things in detail during the UDP lecture. So A will be using any random port. Say in this example, A is using this port number 7576. So the source port number for the packet that is going from A to B will contain this header information. This is the 16-bit of 7576 and the destination port number would be 80 because it's sending a request to B and B is a web server, and because it's listening on port number 80, so the destination port number would be this. So whatever packets are created that will go from A to B, the first two header field, this source port will contain this number, this destination port will contain this number. So it will be for all the packets that is going from A to B in that particular session. So if 50 packets are going from A to B, all these 50 packets will have this source number and all these 50 packets will have this destination port number. Now whenever reply is coming from B to A, because it is sending some request to B, B will obviously reply. It will because it's a web server, it will send some web pages, and all the packets that will be coming from B to A, just this will be reversed. So whenever data will come from B to A, the data packet, this source port, when data is coming from B to A, this time this source port number will be 80 because it's coming from B to A. So in this case, this number would go into this field, source port number, and this destination port number would go in the other field, the destination port number. So from one side to other side, this is one thing, and from the other side to this side is the opposite thing. So this will be very clear, source port and destination port. Why do we use source port and destination port? We use for multiplexing and demultiplexing. And if you do not know what multiplexing and demultiplexing is, again, I request you to go to the lectures of UDP to understand what this is. So we have discussed these two, source port number and destination port number. Let's also quickly discuss the one which is similar as in UDP. This is the checksum field. Now, if you remember, checksum field is used for error detection. If you remember how checksum was calculated, it was calculated by adding all the 16-bit numbers in the UDP packet. Same case, we take all the 16-bit information. This source port 16-bit, destination port 16-bit, sequence number is of 32-bit, so 16-bit from here, 16-bit from this side. Again, for the acknowledgement number, 16-bit from this side, 16-bit from this side. All the 16 bits, all the 16 bits, all the 16 bits, all this 16-bit if options is there, and also the data part, all data part divided into 16-bit words, and then taking some information from the IP pseudo header also. All this information taken together, added together, and then we take the ones complement sum and then we insert in the checksum field. This we have discussed in detail in the UDP. So we'll not discuss it here again. Please go through the lecture of checksumming, how checksumming is done using UDP. The information is exactly similar. The process is exactly similar, how checksum is calculated. Only the data will be different. In UDP, the data was taken from the UDP segment. In this case, we take data from this TCP segment. The IP pseudo header is same. Sorry. The IP pseudo header is same, so the same process, the way how we calculate checksum in UDP, the same way it is calculated here also, and then the result that is obtained, that particular result is inserted in this checksum field. So please go through the discussions in the that was done during UDP about checksumming. The process is absolutely similar, there is no difference. Next we will discuss this header length field. If you look at it, there is a field called header length. This is of size 4 bits. This header length indicates the size of the header. As simple as that. Whatever be the size of header. Remember, if option field is not present, the size of the header is 20 bytes. If option field is present, the size of the header will vary depending on how much data we have inserted in the option field. Now, first thing, why do we require the header length field? Simply because the TCP header field is variable of variable size. And because it's a variable size, we should know exactly where the data field starts. So if it is 20 bytes, we know that the data starts after 20 bytes. If the header size is of 30 bytes, because option field is there, that means the data field starts after 30 bytes of header information. So we use this header length to indicate the size of the total header fields in this particular packet. But there is a catch. The catch is that this header field specifies the length of TCP header in 32-bit words. Now what does it mean? It simply means how many 32-bit words are present in the TCP header, that's all. It does not specify something like 2 bytes or 3 bytes or 4 bytes. It specifies in terms of 32-bit words. What does it mean? Say option field is not present. Say this option field is not present. Option field is 0. Then how many 32-bit words are there in the header part? Source port is 16-bit, destination port is 16-bit. So 16 plus 16, 32. So this is the first 32-bit, one 32-bit word. Sequence number size is total 32 bits. So this is the second. That means we already have two 32-bit words. Acknowledgement number is another field of 32 bits. This is the third 32-bit word. This whole thing, this is of another 32 bit. This is the fourth 32-bit word, and this part is again another 32-bit word. This is the fifth 32-bit words. So if there are no options field, how many 32-bit words are there? 5. So what would be the value in this header length field? It will be 5, the binary value of 5. If I have a binary value of 5 here, it means that there are 5 32-bit words. Clear? So it should be very simple. Now remember, the minimum header size is 20 bytes, maximum header is of 60 bytes. Now we have already mentioned that this option field is rarely present, so most of the time the header size is 20 bytes. And remember, because we have already discussed, since only 4 bits are used to indicate the header length, we have the scaling factor of 4. Remember, 32 bits 32 bits. How many bytes? 4 bytes. 32 bits or 4 bytes. So basically this is a scaling factor of 4. So if you are asked to provide the header length field, what is the value of the header length field? You should actually divide the actual header length divide by 4. So if I have 20 bytes without the option field, what would be the value in the header link field? That means 20 bytes divided by 4 is equal to 5. So we have already seen here 5 32-bit words. So when I have 20 bytes of header information, the value here would be of 5. So if I have more information in the option field, subsequently the size will vary. So just for an example, say if there are no options, the header field contains the decimal value of 5. Why 5? Because 20 bytes of header information without options divided by 4, 5. So this is the value in the header length field. If I have say 40 bytes of header information, 40 bytes means 20 bytes I already have, and say there are 120 bytes of header information. So I have total 40 bytes of header. So I divide it by 4, and what is the value? The value is 10. So what will go in the header length field? The header length field of that 4-bit size will contain this data. If I have the complete options present, that means 40 bytes of option is present. Now my total header size is 60 bytes. So what will go in the header length field? It will be 1111. Why 1111? Because I have 60 bytes of total header field information divided by 4, it's 15. So if I am given the total size of the header length, I can easily find what would go in the header field. If I am given the header length field, if I given a header length field say 1011, and I am asked how many what is the size of the header in that particular packet, I simply need to convert it to a decimal and then multiply it by 4. So I hope this should be clear. The header length field indicates the size of the header, but this is done in 32-bit. How many 32-bit words are there? So we have discussed one more field, the header length field. So what we have discussed till now, we have discussed source port number, we have discussed destination port number, we have seen header length, we have already seen checksum also. Next we will discuss these two important fields known as sequence number and acknowledgement number. We have already discussed why sequence number is required when we were designing our reliable data transfer protocol. Remember, this sequence number and acknowledgement number, these are critical in providing TCP's reliable data transfer service. Without these two fields, it is impossible to provide the reliable data transfer service of TCP. Now both of these fields are of 32-bit size. That means all sequence numbers are represented using 32 bits. All acknowledgement numbers are represented using 32 bits. Now how TCP uses sequence number and acknowledgement number? To understand that, we have to keep in mind that TCP views data as an unstructured but ordered stream of bytes. What does it mean? Let's take a simple example. Say 1000 bytes have arrived from the application layer to the transport layer. Now for this transport layer, it is immaterial what that data means. That means whether the data is coming from a browser, it is a request for a web page, or it is a request for some file, or is itself a file, it is a media file, whatever it is. The content, the meaning of the data is meaningless for transport layer. It does not see what that data is. Again, it's immaterial for it. It simply sees it as a data. And what type of data? As an ordered stream of bytes. That means when 1000 bytes are coming, that means they're coming in sequence, first byte, second byte, third byte, like that, up to 1000 bytes. So for TCP, they are a sequence of bytes, a stream of bytes coming. They are unstructured. Unstructured means they have no meaning for it, but they are ordered. Ordered means first byte, second byte, third byte, fourth byte, like that. Now TCP uses this information, this view, while using sequence numbers. What does it mean? That means till now we have been discussing that we have discussed that TCP puts a sequence number. We have not seen what sort of sequence number it puts. We have just simply assumed that it puts sequence number like first packet number 1, second packet number 2, third packet number 3, then 4, 5, something like that. But in reality, TCP does not use this sort of sequence numbers. It does not put serial numbers like 1, 2, 3, 4, 5 as sequence numbers. It uses this view of data that comes from application layer. What view? It views the data as stream of bytes, and then it numbers those bytes and then use those numbered bytes as the sequence number of the packets. I guess this is difficult to, it will be difficult for you to understand without an example. Now we'll take an example. This is a very easy concept, but this is a very critical concept also. But before explaining that concept, why do we think TCP does not use sequence number like normally 1, 2, 3, 4, 5? Can you think? I'll not give you the answer. I'll give the answer in the subsequent lecture. But today think why TCP does not use normal sequence number like 1, 2, 3, 4. Why does it uses a different concept of sequence numbers, which we'll discuss right now. So think of it. We'll discuss in the subsequent lecture. But let's see how TCP actually use sequence number and what is acknowledgement number. Now we have seen that TCP views the data that is coming from the application layer as a sequence of bytes. Now let's take an example to understand this view. Say the application layer sends 1000 bytes of data to the transport layer to be transmitted using TCP to the other side. Now as we have discussed, TCP will not look for the meaning of these bytes. It does not see from what application is coming. It simply sees that the data has come from the application layer. Now how many bytes have arrived? 1000 bytes. Say this is the first byte, this is the second byte, this is the third byte, this is the fourth byte, this is the fifth byte. Like this, how many bytes? 1000 bytes. Clear? 1000 bytes of data has come from the application layer. This should be clear. Okay. Now TCP sees them as a stream of bytes. So this is a stream of bytes, one after another. They are unstructured, that means they do not have meaning, but they are a stream of bytes. Now TCP numbers these bytes. Say the first byte number is 0, just for an example. The first byte number is 0. The second byte number is 1. The third byte number is 2. Then the fourth byte number is 3, fifth byte number is 4, and like that the 1000 byte number will be 999. So in this example I have 1000 bytes of data coming from the application layer. TCP marks these bytes with some numbers. Say it starts from 0, this is the first byte number is 0, the second byte is 1, then 2, 3, and so on. So because there are 1000 bytes, the last byte number is 999. Now assume that because of limitation of MSS, say 4 packets has been created. Say 4 packets have been created. That means 1000 bytes of data has to be inserted in 4 packets. Clear? Why 4 packets? This is a random example. 4 packets because the MSS is say 250 bytes. That means maximum 250 bytes of data that can be inserted in the data part. Now first packet will contain 250 bytes of data. Second packet will contain under 250 bytes of data. Third packet will contain under 250 bytes of data, and fourth packet will contain under 250 bytes of data. Total 1000 bytes. Look at the first packet. First packet. Which data will be there? The byte that starts from number 0 to 249. Simple. It starts from the byte number 0 to the byte number 249. Why up to 249? Because only 250 bytes of data can be placed. Same way, second packet, which numbered bytes should be there? Second packet. So starting from byte number 250, it will start from byte number 250 up to total again 250 bytes. So under 250 bytes, that means up to 499. So starting from byte number 250 to byte number 499, this numbered bytes will be present in the second packet. What about the third packet? Third packet, it starts from byte number 500. It will go up to 749. Sorry, 749. And in the fourth packet, the byte numbers will be from 750 till 999. So the first packet will contain from byte from number 0 to 249, second packet will contain byte from 250 to 499, third packet 500 to 749, and fourth packet from 750 to 999. Now remember, we are discussing sequence number. Now what TCP does is, it insert the number, the byte number of the first byte number as the sequence number, the number of the first byte of that packet as the sequence number. Listen to it carefully again. TCP will use the byte number of the first byte in the packet as the sequence number of that packet. That means for the first packet, the sequence number would be 0, because 0 is the byte number of the first byte in that packet. Clear? In this example, the sequence number of the first packet would be 0. Clear? So sequence number is of 32 bits, so 32 zeros. The sequence number of the second packet will not be, it will not increase like 0, 1, 2, 3. Now the sequence number of the second packet will be 250. Clear? That means why 250? This is the number of the first byte in this particular packet. This number is used as the sequence number. So in the same way, the sequence number of this third packet would be 500. So what will be placed in the sequence number of the third packet? The 32-bit binary representation of this number 500. And for the fourth packet, the sequence number would be 750. Sorry, 750. Clear? This is a very important concept. The sequence number does not increase by value like 1, 2, 3, 4, something like that. It increases. The sequence number is basically the number of the first byte of that particular packet. So in this example, the sequence numbers are 0, 250, 500, and 750. Ensure that you have understood this concept. Now remember, we have simply told that in this example, we have seen that the sequence numbers are numbered like the first is numbered 0, the second 1, 2, 3, like that. It is again not required to be numbered as starting from 0. The first number can be anything. In fact, later on in the next lecture, we will see that the first sequence number should be in fact a random number. It should not be something starting from 0. Why a random number, we'll discuss in the next lecture. It's again a very important concept. But say the first byte has been numbered any random number, say something like 720. Clear? Any random number. So the next byte will be numbered 721. The third byte will be numbered 722, then 723, 724. Like this. So it will go on. So now these bytes are numbered starting from 720. So it will go up to 1719. That means total again 1000 bytes. But we have not started numbering from 0. We have started numbering from 720, a random number. Now what happened? So the first packet will contain starting from byte number 720 to another how many bytes? Total 250 bytes. Clear? So it will start from 720, and you can simply add another 249. Let's start the calculator and see, it will be say 969. That means again total 250 bytes. Clear? I think it should be now clear. So the first packet, instead of starting from 0, it starts on 720, but again total how many? Total 250 bytes. So the sequence numbers of this packet will be 720. This our sequence number of the first packet is 720. The second packet, same way you do this part. So this will start from 970 under 250 bytes, whatever will be, but the sequence number of the second packet will be 970. So same for the third packet, same for the fourth packet. So I hope by now we have understood how these sequence numbers are inserted in the TCP header. They are not normal sequence numbers like 1 2 3 4. They are sequence numbers which indicates the first number, the number of the first byte of that particular packet. What does it mean by the number? The number means all the data, all the bytes that are coming from the application layer, they are viewed as a stream of bytes, and each of the byte is numbered. The number can start from any random number, clear, and whatever be the stream of bytes inserted in the packet, the number of the first byte of the packet is the sequence number of that particular packet. The first byte number is always random. Why this is random we'll see in our subsequent lecture, but again you also think why this number should be random. This is a very interesting question. A lot of research has been done how this number can be really randomized. But before that you have to understand why a random number is used as for the first byte and increase subsequently like this. But anyway, I hope you have understood how sequence numbers are used in the TCP packet. Now let's understand what is the meaning of acknowledgement number. Once you have understood the sequence number, let's see acknowledgement number. So say A have sent certain packets to B. So say the sequence number of the first packet is say 10. Just for an example, first packet sequence number is 10. The second packet sequence number is 20. The third packet sequence number is 30. The fourth packet sequence number is 40. Just for an example, fifth packet sequence number is 50. That means each of this packet contains 9 bytes of data. So first packet contains byte number starting from 10 to 19. Then second packet contains byte number from 20 to 29. Let's indicate the byte number 10 to 19, 20 to 29, 30 to 39, 40 to 49, and 50 to 59. These are the byte number that are being sent. So the sequence number for this first packet is 10. Sequence number for the second packet is 20, and so on. The third is 30, 40, 50, like that. So these packets are sent to the other side. The first packet goes and it arrives at the other side. Clear? I say this other side name is B. B receives packet 1. Now it has to send an acknowledgement. We have already seen acknowledgement sent. When we were designing the reliable data transfer protocol, we see that for the packets it sends an acknowledgement. Now B receives packet 1 and it sends an acknowledgement. What does B indicate in the acknowledgement field? Now this is the important part. The acknowledgement field, we're discussing two fields, sequence number field and acknowledgement number field. So B is sending an acknowledgement. Now it puts certain number in the acknowledgement field. What does B receives in the acknowledgement field? B puts in the acknowledgement field the next value, the sequence number of the next packet it is expecting. Listen to it again. B will insert in the acknowledgement number field the sequence number of the next packet it is correctly expecting. So B has received the first packet. The packet contains byte from 10 to 19. So what would be the sequence number of the next packet it would be expecting? The next packet it would be expecting has a sequence number of 20. So it will put the value of 20 in the acknowledgement field number. It will simply convert 20 into binary, take the 32-bit representation of 20, and then it will insert in the acknowledgement field, that header field, acknowledgement number. Clear? So A sends a packet to B. When B sends an acknowledgement, in the acknowledgement field, it will insert the sequence number of that packet which it is expecting next. So B receives the next packet. B receives packet 2. B receives packet 2. Clear? Now it sends an acknowledgement. Now in the acknowledgement field, what it will put? It will insert the value 30. It will insert the binary value, the 32-bit binary value of 30. Why it will indicate 30? That means I have received up till byte number 29. When B sends an acknowledgement to A with a value of 30 in the acknowledgement number field, it indicates that I have received the bytes up till 29th. Next, I am expecting byte number starting from 30. That means next I am expecting a packet which has a sequence number of 30. Clear? So this should clear your concept of acknowledgement number, a sequence number and acknowledgement number, how a sequence number increased and what is inserted in the acknowledgement field number. Now let's assume that the third packet got lost. Third packet got lost. Clear? Now B receives fourth packet. B receives packet number 4. Now it was expecting packet number 3. It was expecting a packet with sequence number 30, but it receives the packet with sequence number 40. Now it needs to send an acknowledgement. It needs to send an acknowledgement because it has received a packet. What does it insert in acknowledgement number? Now this is important. Now in the acknowledgement number field, it will insert the acknowledgement number which it is expecting correctly. It received packet number 1, it received packet number 2, third packet get lost. It was expecting a packet which is sequence number 30, it did not arrive. It received a packet with a sequence number 40. What was it expecting? It was expecting packet number 30. So it will send an acknowledgement with a acknowledgement number of 30. That means I am expecting a packet with sequence number 30. Clear? Say after some time we receive fifth packet also. A fifth packet. It has still not received the third packet, so it will send an acknowledgement number for 30. That means I have received certain packets, but I'm expecting a packet with sequence number 30. Now, say after some time, timeout occurred for the third packet, and A retransmits packet third, and after some time, say B received packet 3. Clear? It was expecting packet number 3. Clear? Now this is important. What does it do next? Depend on what flavor it is using. Clear? Now if it is using go back and strategy, obviously A has to retransmit all this packet 3, 4th and 5th. Clear? If it is using selected repeat, it was buffering packet number 4th and 5th. Clear? So you can A need not retransmit packet 4th and 5th. Now when A resend packet number 3rd and B receive packet 3, it was expecting a packet with sequence number 30. Now it has received. Now you can actually send an acknowledgement, and the acknowledgement number will contain the number 60. Why 60? Think clearly. It received packet 1, it received packet 2, it was expecting third packet with a sequence number 30. It received fourth packet, but it was expecting packet third with a sequence number 30. So in this case, it sent an acknowledgement 30. Clear? In say, and it buffered packet number 4th. It received the 5th packet, it buffered packet 5th also, but it sent an acknowledgement of 30, saying that I am still expecting packet with a sequence number 30. Now when it received the packet 3rd due to a retransmission, now it sends an acknowledgement of 60, which indicates that I am sending a cumulative acknowledgement. What is a cumulative acknowledgement? If you do not know, go back to the lecture of go back and select the TCP. It simply says that I have received up till byte number 59. That means I have received packet 4th also, I have received packet 5th also. It is not individually acknowledging packet number 4th. By simply saying acknowledge number 60, it means that up till number 59th I have received. The next sequence number I am expecting is a packet with sequence number 60. That means if there is 6 packet, it is expecting that packet. Clear? So it did not send an acknowledgement for the 4th packet, it did not send an acknowledgement for the 5th packet individually. By simply saying acknowledgement equal to 60, it means that I have received all bytes up to byte number 59. So in the acknowledgement number, it simply insert the value 60, indicating that next it is expecting a sequence number, it is expecting a packet with sequence number 60. It's a very, very interesting concept. So I hope you have understood the concept of sequence number and acknowledgement number clearly. Remember, the concept of sequence number and acknowledgement number is very, very critical in the working of TCP. In the way how it provides reliability depends a lot in the use of the sequence number and the acknowledgement number. So we have discussed two very important concepts of sequence number and acknowledgement number. You should understand how sequence numbers are created and what is inserted in the acknowledgement number field. These two concepts are, again, as I have told, are critical in the working of TCP. In the next class, we'll discuss about these fields. You see there are 6 1-bit fields. These are known as 1-bit flags. We'll discuss these flags in the subsequent lecture. And during the discussion of these flags, we'll discuss the important concept of TCP connection establishment. And later on, we'll discuss this header field known as receive window, which is used for flow control. Clear? And again, all these discussions we have been doing are based on the textbook Computer Networking, a top-down approach by Jim Croce and Keith Ross. So that's all for today, and we'll meet you in the next lecture. Till then, thank you and goodbye.